So today we are going to learn about derivatives. Not only derivative, we are going to learn about higher order derivative in this particular case. So I think we have learned what a function is, that is y equal to fx, and we know how to derivate it the first time, that is dy by dx equal to f prime x. If we derivate it the second time, of course we get d2y by dx2 equal f double prime x. Now there is this series that is going on and on and on and on. Alright, so that's how we calculate higher order derivatives. Simple. Is that it? Well, if that is so, then I give you this function and I want you to calculate the fourth derivative of this function. Alright, if you do it in a conventional way, this is going to take all of your day, and within a given period of time you're never going to make it. So what you should do is you should calculate special formulas to calculate derivative of some special functions so that you can use these formulas whenever the time demands. So our topic is higher order derivatives, and we will be learning to calculate the higher order derivatives of some special functions, and also there will be 10 special functions, and we'll induce formulas to calculate higher order derivatives of each of these functions. So let's start with the first one, the very simple one, that is y equal x power n. Now in order to calculate a formula or induce a formula that applies to general higher order derivatives, what we do is we suppose a function that looks just like this, which is y equal x power 4. Now if we derivate this function for the first time, or the first derivative will be 4x cubed, the second derivative will be 12x squared, the third will be 24x, and the fourth will be 24, and if we try to do the fifth it will be 0, so we don't go there. Now I want you to look at the pattern of these derivatives. I want you to closely observe what is happening here. So let's observe the first one and the last one. What do we see? Do we see some relationship here? Of course, the first one has x power 4 and the last one is 24. So there is a relationship between 4 and 24. Can you figure it out? Yeah, those of you who have figured it out, congratulations, you have done pretty well. The relationship between 4 and 24 is 4 factorial is 24. So as we see this pattern, we should think that the general formula has something to do with factorial, right? So the formula or the general formula is going to rotate around factorials. Now I want you to look at the third or the second derivative or the third number of the right one, which is the second derivative, that is 12x squared. You can see that as this is the second derivative, I want you to look at the power of x. It has power of x as 2. The first function had the power of x as 4. So as we go to the second derivative, the power has decreased by 2 times, bringing it to x power 2. So simply the nth derivative can be written as x power m minus n, where n is the nth derivative of the given function. So m is simply 4. So 4 minus nth derivative, that is the second derivative, is 4 minus 2 is 2. So we get the power of x as x power 2. Now we should deal with the constants. So as we have said, the constant has to do with factorial. So what is the relationship is that if we try to observe this and apply mathematical induction here, we get that the constants are related to each other with some formula that is like this. This is m factorial by m minus n factorial. So m is simply 4. So let's try to test it in the second derivative. So the second derivative, we see the value of m is 4 factorial, and we get in the upper part we get 4 factorial, in the down part we get 2 factorial. 4 factorial by 2 factorial is simply 12. Now if we combine these both terms here, we get a generalized formula for the nth derivative of the given function, that is yn equal x power m minus n times m factorial divided by m minus n factorial. So this is what we are looking at. This is the final shot. Okay, so now we want to go at the next formula, which looks just like this, but it is slightly different. The difference is that it has a constant that is before x, which is a, and after the x we have added a constant that is b, and we have given it a whole bracket and we have raised it to the power of n. So now this looks similar to what we have just seen here, alright? But there is a difference in this particular case. The difference is this, the constants. Now, if we deal with the constants in this case, then we are going to solve this particular problem with the help of the previous one. So let's try to derivate this function for the first time. What do we get? We get an expression that looks just like this. I think you have used these expressions previously while doing simple order derivatives or the first order derivatives. You can see here that dy by dx, we get dx plus b power n. So in order to derivate a function like this, we have to make the down part the same as the upper part. We get dx plus b, and if we individually try to differentiate dx plus b, then we get something like that. So as you can see in the back part, the part or the first part, dax by dx, will be solved as a, and dv by dx will be solved as 0, so which will look like a plus 0. So every time we derivate this type of function, we always repeat this pattern. That means we always do the back part, that is dx ax by dx plus db by dx. We always solve this part. For nth derivative, we continue this part for the n times. So therefore, the constant that is coming out, which is a, will always come every time we derivate the function. So what we get here is a will be the function of n, and as we repeat the a n times, we'll get a power n. So this is just simple common sense and logic. I hope you understand what I'm saying, because you have already practiced derivatives in the previous classes. Now, if we just compare the function that we have just dealt with previously, that has just appeared in the screen, and the previous function, they're just similar. The only difference between them was the constants, and as we have already dealt with the constants, now there is nothing to worry about the part, because we can consider x plus b simply as x. So we knew that the derivative of the previous function was x power m minus n m factorial by m minus n factorial. The derivative of this part will be m factorial by m minus n factorial. So instead of x, we will replace x with ax plus b. I'm very sorry for the error here. It should be m minus n, and we get an external part that is a power n here. Alright, so that's it. So this is the final shot, and this is the final formula of what we were calculating. Now we go to the next function, and the next function is y equal a power ax. So I think we have already dealt with y equal e power x. How many times we derivate y equal e power x? We will always get e power x. So e power x is such a type of function. But since the constant a has appeared here, it brings us some problem, but the problem will soon be resolved. So let us derivate this function for the first derivative. We get d power x by dax times dax dx. So what we evaluate from here is this. If we derivate the first part of this function, it will always be e power x. So the e power ax, so the e power ax will not change. What will change here is dAx by dx. So every time we derivate dAx by x, dAx dx with the help of every time we derivate dAx with the help of dx, we always get an extra term, that is a. So the extra term a will appear every time we derivate the function. So this time also it will be just similar to what we have previously learned, is that a will be the function of the n, and therefore a power n will be the final result. So we get a combined formula for this given special function, that is y, the nth derivative of y is given by e power ax times e power of n. So thank you everyone. This was for today. I would like to end our course. We will learn further special functions in our next videos.